Welcome, my friends. In this video, I will use the law of sines to solve non-right triangles. The law of sines and the law of cosines can be used to solve for oblique triangles, which is just another word for non-right triangles. Remember that to solve a triangle means to find all of the angles and all of the side lengths. If we have a right triangle, we can use SOHCAHTOA, the Pythagorean theorem, and the idea that the interior angles of a triangle sum to 180 degrees to solve a triangle. We've done that in other videos. But if we have an oblique triangle, which is just a non-right triangle, that means we can't use SOHCAHTOA or the Pythagorean theorem. We have to resort to other methods, such as the law of sines and law of cosines. The one tool that worked for right triangles that also works for oblique triangles is the interior angle sum theorem. We can still use the fact that the interior angles of a triangle add up to 180 degrees for an oblique triangle. Now, in order to solve a triangle using the law of sines or law of cosines, you need to know three things about that triangle. You need to either know two angles in one side, two sides in one angle, or three sides. As long as you have one of those cases, you should be able to use either the law of sines or law of cosines to solve the triangle. Let's talk about each of those specific cases. The first type of triangle that you should use the law of sines for is what we call the SAA triangle. This means that you are given one side and two angles of the triangle. If that's the case, you can use the law of sines to solve the triangle. The first thing you would do is find the missing angle using the idea that the interior angles of a triangle should always sum to 180 degrees. From there, you can use the law of sines to solve the remaining sides. The second case, where you would use the law of sines to solve the triangle, is the ASA case. This is very similar to the SAA case, except for the side is between the two angles. You would still find the missing angle using the idea that the interior angles of a triangle should add to 180 degrees, and then you would use the law of sines to solve for the two missing sides. The other case that you should use the law of sines is when you have an SSA triangle. Note that the order of SSA is important for this case. This means you have two sides right next to each other and an angle that is not between them. If the angle is between the two sides, then you have a different case. So as you can see here on this triangle, we have two sides and we have an angle, and that angle is not between the two sides. If you had an angle that was between the two sides, that would be an SAS triangle, which would be dealt with the law of cosines. Now, there are two other cases that should be solved not with the law of sines, but with the law of cosines. The first is very similar to this case, but the difference is now the angle is between the two sides. This is what we call the SAS triangle. If you have two sides of the triangle, and you also have the angle that is between those two sides, then you have an SAS triangle, which should be solved using the law of cosines. The final case is the SSS triangle. If you have all three sides of the triangle, you can solve the triangle using the law of cosines. For the remainder of this video, I will introduce the law of sines and then practice solving different triangles. Most of my examples will be of the SSA case, because this is the most complicated. The reason this is the most complicated is because we call it an ambiguous case, because there are many possible solutions. You can either get 0 triangles, 1 triangle, or 2 triangles. Every other case, you will always only have one unique triangle, but in the SSA case, you could either have 0 triangles, 1 triangle, or 2 triangles. Why is that the case? Well, it's a little bit difficult to explain, and not extremely important for you to understand in order to use the law of sines. Even if you don't understand why we can have either 0, 1, or 2 triangles, you can still use the law of sines to help you find the answer. But let me give you a brief explanation to hopefully give you some intuition as to why we can have so many different possibilities. Why might the two sides at an angle create a triangle that's not even possible? Well, just imagine for a second that this side is really, really long, and this side is very, very short. It might be the case that this side is too short to make it down to this side. If that's true, then we will not have any triangle at all. Another reason why you might have no triangle at all is perhaps the angle they've given you is already the largest angle. If this is already the largest angle, and the side opposite to that angle is not the largest side, then you know that this triangle is not possible. Larger angles must always open to larger sides. So if this is the largest angle and this side is smaller than this side, then that means that that triangle is not possible. Why might we sometimes have two triangles? Well, since this side is unknown, it's possible that this side is either really short or possibly really long. This angle could be an acute angle, which would make this side shorter, or it could possibly be an obtuse angle, making this side longer. That can sometimes create two separate triangles. Now sometimes in the two triangle case, you might discover that one of the two triangles is impossible. Say that one of the angles that you solved for plus the angle that you already know adds up to something that's already greater than 180 degrees. If that's the case, then that triangle is impossible because we know that the interior angles of every triangle must add up to 180 degrees. So sometimes it appears that you have the two triangle case, but then when you start working on one of the triangles, you realize it doesn't work. So that creates the third case, where you have only one triangle. So again, the three cases for the SSA triangle are either zero triangles, one triangle, or two triangles. Now, that might seem like a lot to remember, and it is. The good thing is, you don't really need to memorize which situations will lead to either 0, 1, or 2 triangles in the SSA case. When you use the law of sines, it will tell you which case you have. I would remember in the back of my mind, though, that when I have an SSA triangle, there are the three possible outcomes, either 0 triangles, 1 triangle, or 2 triangles. And then you won't be surprised as you work through the law of sines when you get 0, 1, or 2 results. Let's talk about what the law of sines says. The law of sines states that the sine of any angle on a triangle divided by the length of the side opposite to that angle will be equal. Typically, we denote capital letters for the angles of a triangle and lowercase letters for the sides. The lowercase letters always correspond to the angle that is opposite to them, so we use the same letter. So we have uppercase A and lowercase a for the side opposite, uppercase B and lowercase b for the side opposite uppercase b, and uppercase C and lowercase c. The formula is sine of capital A, meaning sine of this angle, divided by the side opposite, is equal to sine of uppercase b divided by lowercase b, which is also equal to sine of uppercase c divided by lowercase c. Now I'm giving this to you all as one formula, but in reality you will always only use two pieces at a time. For example, perhaps you would use sine of capital A over lowercase a is equal to sine of uppercase b over lowercase b without the sine of c over c. Or maybe you would use the first part and the second part together, or maybe the second part and the third part. You would never use all three all at once. So you would just equate one angle to the opposite side to another angle and the opposite side. How should you choose which two to use? Well, you should choose two ratios such that you know 3 out of 4 values. So for example, if I knew uppercase A, lowercase a, capital C, and I did not know lowercase c, then I would use sine of uppercase A over lowercase a, two values I know, is equal to sine of uppercase C, which I know, divided by lowercase c, which is a value I don't know. Since I know 3 out of 4 values, I can always solve for the fourth. Let's take a look at a triangle. Here we have a triangle with a 122 degree angle, a 25 degree angle, and then a side opposite that angle of 64. Let's label the two missing sides and the missing angle. Let's label the missing angle as capital C. That means the side opposite that angle must be lowercase c. Let's label the side opposite the 122 degree angle as lowercase b. This is a side angle angle triangle, or an SAA triangle. We know one side and two angles. SAA triangles are solved with the law of sines, and specifically, this is the unambiguous case. This is a triangle that will only have one solution. The first thing we should do is solve for the missing angle capital C. Recall that the interior angles of a triangle must always add to 180 degrees. That means if you know two angles, you can always find the third. The way we can do this is by taking 180 degrees and subtracting the other two angles. 180 minus 122 minus 25 is equal to 33 degrees. That means that the missing angle, capital C, is equal to 33 degrees. At this stage, we can solve for the missing side length C and B using the law of sines. I don't really refer back to the formula when using the law of sines. I just remember that sine of any angle divided by the side opposite of that angle will be equal for any triangle. So what we need to do is pick an angle where we know the side opposite. In this case, we know 25 degrees and the side opposite, which is 64. Then we need to pick another angle where we don't know the side opposite. In this case, either the 122 degrees and the B, or the 33 degrees and the C. I'm going to choose to start with the 122 degrees and the B. I know that sine of 25 degrees divided by the side opposite of 64 is equal to sine of 122 degrees divided by the side opposite, which is B. We can cross multiply to solve this. We will have B times sine of 25 degrees is equal to 64 times sine of 122 degrees. If we divide both sides by sine of 25 degrees, we will get that B is equal to 64 times the sine of 122 degrees divided by sine of 25 degrees. If you type this into your calculator and you make sure that your calculator is in degrees, you will get B is approximately equal to 128.4. We can fill this in onto our triangle. The last thing we need to solve for is lowercase c. We can use the same idea. We know that sine of any angle divided by the side opposite is equal on any triangle. So that means that sine of 33 degrees divided by the side opposite, which is lowercase c, must be equal to sine of 25 degrees divided by 64. Instead of using sine of 25 degrees divided by 64, I could have also used sine of 122 degrees divided by 128.4. I prefer to use this value because the 128.4 is rounded, and none of the values here are rounded. Once again, we can cross multiply so that we get c times sine of 25 degrees is equal to 64 times sine of 33 degrees. Dividing both sides by sine of 25 degrees, we get that c is equal to 64 times the sine of 33 degrees divided by sine of 25 degrees. If you type this into your calculator, you will get that c is approximately equal to 82.5. We can fill in the missing side length to our triangle. At this stage, we have solved the triangle. We have all three angles and all three sides. Let's try another problem. In this case, we have two sides and we have an angle, and the angle is not between the two sides. We call this the SSA triangle because we know two sides and the angle is not between the two sides. It's very important to pay attention to if that angle is between the two sides, because if it was, then we would not use the law of sines. Instead, we would use the law of cosines. If you forget if the law of sines or law of cosines should be used, once you try one of them, you will realize whether or not you've chosen the right option. If you choose the wrong option, then you will not be able to solve the triangle. So it's not super important that you remember exactly which type of triangles to use law of sines or law of cosines for, but it can be a little bit helpful when starting. Okay, this is the ambiguous case, where there are either 0, 1, or 2 triangles. SSA triangles either have 0, 1, or 2 solutions. How do we know which case we have? Well, there are sometimes things to look for, but the easiest thing to do is just to apply the law of sines and see what you get. Let's try to solve for the angle capital C. I know 126 degrees and the side opposite. I also know the side opposite of capital C. If that's the case, I know 3 out of 4 things, and I could use those two ratios to solve for capital C. Sine of capital C divided by the opposite side of 24 is equal to sine of 126 degrees divided by the opposite side of 15. If we cross multiply, we will get 15 times the sine of capital C is equal to 24 times the sine of 126 degrees. If we divide both sides by 15, we will get that sine of capital C is equal to 24 times the sine of 126 degrees divided by 15. The way that you solve for an angle in a sine function is to take the inverse sine of both sides. The inverse sine of capital C is just capital C, and the inverse sine of the right-hand side is inverse sine of 24 sine of 126 degrees divided by 15. If you type the inside of the inverse sine function into your calculator, you will get 1.29. Now this is asking us sine of what is equal to 1.29? Well, remember that the range of the original sine function is between -1 and 1. Sine of nothing will give you 1.29, so there is no solution. If you were to type this into your calculator, you would get an error. There is no angle that you can take the sine of that will give you 1.29. Sine ranges from -1 to 1, so there is no solution. There is no possible side-side angle triangle with these side lengths and this angle that can create a triangle. Now, you could have noticed this from the get-go. 126 degrees will be the largest angle of this triangle, because an obtuse angle in a triangle will always be the largest angle. Larger angles must open to larger sides, and in this case, the largest angle of 126 degrees does not open to the largest side. 24 is larger than 15, so we already should have known from the get-go that this was not possible. Let's try another one. We have two sides and an angle, and again, the angle is not between the two sides. This is again what we call the side-side angle triangle, which is the ambiguous case, with either 0, 1, or 2 solutions. Let's try to solve for capital C. Sine of 29 degrees divided by 52 is equal to sine of capital C divided by 65. 29 degrees and 52 are opposite of each other, and capital C and 65 are opposite of each other, so this works with the law of sines. If we cross multiply, we will get that 52 sine of capital C is equal to 65 times sine of 29 degrees. If we divide both sides by 52, we will get that sine of capital C is equal to 65 sine of 29 degrees divided by 52. If we take the inverse sine of both sides, we get that one of the possible values for C is equal to inverse sine of 65 times the sine of 29 degrees over 52. The reason that this is only one of the possible outcomes, and I've labeled this as C1, is because inverse sine actually only gives you one of two possible outcomes on one revolution of the circle. There are generally two times when you have any given y-coordinate on the unit circle. Inverse sine always gives you an angle that is either in quadrant 1, which would be positive, or in quadrant 4, which would be negative. Dealing with the law of sines in problems like these, you will typically have a positive angle, meaning you will have an angle in quadrant 1. There will be another angle in quadrant 2 that has the same y-coordinate, or the same sine, and you need to also solve for that angle. Firstly, if you plug this into your calculator, you will get 37.3 degrees. That is one of the possible angles for C on our triangle. But there's also another angle. Now 37.3 degrees is somewhere around here. But there's another angle on one revolution of the circle that gives you the same y-coordinate. That would be 180 degrees minus 37.3 degrees, or 37.3 degrees above the negative x-axis. If we take 180 degrees and subtract 37.3 degrees, we will be at 142.7 degrees, which would be around here. This angle would have the same y-coordinate on the unit circle as 37.3 degrees, and therefore sine would be equal. So we really have two different options. Either C is equal to 37.3 degrees, or potentially C is equal to 142.7 degrees. These are both valid solutions. C could either be equal to 37.3 degrees or 142.7 degrees. We will have to make two separate triangles to account for the two possible answers. Let's focus on the first triangle, which will have a C of 37.3 degrees. If that's the case, we can solve for capital letter A, because we know the interior angles of a triangle must always add to 180 degrees. We can find A1 by taking 180 degrees and subtracting the other two angles. If we subtract 29 degrees and 37.3 degrees, we will get that A1 is equal to 113.7 degrees. We can place this angle onto our triangle. We can use the law of sines again to solve for lowercase a. Sine of 29 degrees divided by the opposite side of 52 is equal to sine of 113.7 degrees divided by the opposite side of lowercase a. I'm labeling this lowercase a1 because this relates to our first version of the triangle. There will be a second triangle we will have to solve for later. If we cross multiply, we will get a1 times sine of 29 degrees is equal to 52 times sine of 113.7 degrees. If we divide both sides by sine of 29 degrees, we will get that a1 is equal to 52 times the sine of 113.7 degrees divided by sine of 29 degrees. If we type this into our calculator, we should get that a1 is approximately equal to 98.2. We can place this side length onto our triangle. At this stage, we have solved for our first triangle. All we have to do now is solve for the second triangle, which has an angle C of 142.7 degrees instead of 37.3 degrees. In our first triangle, the angle C was equal to 37.3 degrees. In our second triangle, we took 180 degrees and subtracted this angle to find the angle that would be part of the second triangle, 142.7 degrees. We can place this angle onto our second triangle. Now we can solve for uppercase A using the idea that the interior angles of a triangle should add up to 180 degrees. A2 is equal to 180 degrees minus 142.7 degrees minus 29 degrees, which is equal to approximately 8.3 degrees. We can place this value onto our triangle. At this stage, we can solve for lowercase a sub 2. Sine of 29 degrees divided by the opposite side of 52 is equal to sine of 8.3 degrees divided by the opposite side of A2. If we cross multiply, we will get that A2 times sine of 29 degrees is equal to 52 times sine of 8.3 degrees. Dividing both sides by sine of 29 degrees, we will get that A sub 2 is equal to 52 times the sine of 8.3 degrees divided by sine of 29 degrees. If we plug this into our calculator, we will find that A2 is approximately equal to 15.48. We can place this value onto the triangle to finish our second triangle. This is the second possible solution for our triangle. Now, of course, this is not drawn to scale. If I was to draw this a little bit more accurately, this is what that triangle would look like, with the angle C being a much larger angle than the other two. Let's try another one. Here we have another side-side angle triangle. We know two sides, and we know the angle that is not between the two sides. If the angle was between the two sides, then we would have the side-angle-side triangle, which should be solved with the law of cosines. Instead, we have two sides and an angle that is not between them, so we have the side-side angle triangle. We can't solve anything related to C quite yet, because we don't know the angle, capital C, or the side opposite of that angle, lowercase c. We would have to know one or the other to use law of sines. We can, however, use the law of sines to solve for capital A. Sine of 33 degrees divided by the side opposite of 63 units is equal to sine of capital A divided by the side opposite of 60 units. We can cross multiply to get 63 sine of A is equal to 60 times sine of 33 degrees. If we divide both sides by 63, we will get sine of A is equal to 60 times the sine of 33 degrees divided by 63. If we take the inverse sine of both sides, we will get A on the left-hand side, since the inverse sine of sine of A cancels the sine, and on the right-hand side, we will get the inverse sine of 60 sine of 33 degrees divided by 63. If we plug this into our calculator, we will get one possible value for A as 31.25 degrees. We can place this angle onto our triangle. Now, just like last time, inverse sine is only going to give us one of two possible solutions on one rotation to the circle. We have a solution that is in quadrant 1, but we know that there will be another time in quadrant 2 where the y-coordinate on the unit circle, which is what sine is, will be the same. Specifically, we would have to be 31.25 degrees above the negative x-axis. The way we find this is by taking 180 degrees and subtracting 31.25 degrees. We will get 148.75 degrees. If you're confused about finding the second angle, if you're using the law of sines, it will always be 180 degrees minus the angle that you already found. So in our case, 180 degrees minus 31.25 degrees is equal to 148.75 degrees. Let's work with the first angle that we already found of 31.25 degrees. If that's the case, we can solve for uppercase C by using the idea that the interior angles of a triangle always add to 180 degrees. 180 degrees minus 33 degrees minus 31.25 degrees is equal to 115.75 degrees. So that is our last angle. Now I'm going to take a moment to find what C2 would be equal to. C2 would be equal to 180 degrees minus the 33 degrees that we already had minus 148.75 degrees, because that is our other option for A. If we do this calculation, we will have 180 degrees minus 33 degrees minus 148.75 degrees, which is equal to negative 1.75 degrees. But of course, we can't have a negative angle on a triangle, so that means that there actually is not a second possibility for this triangle. the second angle that we found of 148.75 degrees does not leave us with enough degrees to create a triangle. So therefore, there is only one triangle. There will only be one solution to this problem. The second solution does not work. Okay, let's continue with our first solution related to C1. At this point, we can solve for lowercase c using the law of sines. Sine of 115.75 degrees divided by the opposite side, which is lowercase c, is approximately equal to sine of 33 degrees divided by 63, the opposite side. I say approximately equal to because 115.75 degrees was already rounded. If we cross multiply, we will get c times sine of 33 degrees is equal to approximately 63 times sine of 115.75 degrees. If we divide both sides by sine of 33 degrees, we will get that c is approximately equal to 63 times the sine of 115.75 degrees divided by sine of 33 degrees. If we enter this into our calculator, we will get that c is approximately equal to 104.19. We can put this onto our triangle. This is the only solution. Since we did not have two solutions, this is the only possible triangle that is a solution. Okay, let's look at one final problem, which will be a word problem. Two major airports in New York City are LaGuardia Airport and JFK International Airport, which are only 9.5 miles apart from each other. Suppose an airplane is flying somewhere on a straight path between the two airports. The angle of depression from the plane down to LaGuardia is 75 degrees, and the angle of depression from the plane down to JFK is 54 degrees. Find the distance from the plane to the JFK International Airport. Here's the picture of the situation. We have the plane right here, which has a 54-degree descent down to JFK, or a 75-degree descent to LaGuardia. The distance between the two airports is 9.5 miles. Let's represent the side lengths and angles on the triangle with letters. We have capital A, capital B, capital C, lowercase a, and lowercase b. Our goal is to find the distance from the plane to JFK International Airport, so we are trying to find lowercase a. Now right now, we only know one side. In order to use the law of sines to solve a triangle, we'd have to know one side and two angles, or two sides and one angle. Perhaps we can use these two given angles to solve for two of the angles of the triangle. Now we know that an angle related to a straight line is 180 degrees. That's kind of like having half a circle. Therefore, the angles 54 degrees, 75 degrees, and capital C must add up to 180 degrees. So we can solve for the angle capital C by taking 180 degrees and subtracting the two other angles. We will get 51 degrees, so capital C is equal to 51 degrees. Now the other two angles are a little bit more difficult to solve for. We can use this image right here to help us out. If we have two parallel lines, kind of similar to what we have here, with a transversal crossing the two parallel lines, kind of like this side of our triangle, then we know that many of the angles are equal to each other. Angles 1, 4, 5, and 8 are equal, as well as 2, 3, 6, and 7. 54 degrees is in the position of angle 3. B is in the position of angle 6. We know that 3 and 6 are equal to each other, so therefore angle B must be equal to 54 degrees. The term for this is alternate interior angles. Angles 3 and 6 are alternate interior angles, and are therefore equal to each other. Now, we could solve for the missing angle using the idea that the interior angles of a triangle must sum to 180 degrees, or we can use our image. 75 degrees is in the position of angle 4. A is in the position of angle 5. Angles 4 and 5 are alternate interior angles, and will therefore be equal, so therefore angle A must be 75 degrees. At this point, we have all of the information we need in order to find the distance from the plane to JFK International Airport. We have three angles and one side. As long as we have two angles and a side, we can use the law of sines to solve for a missing side. In this case, sine of 51 degrees divided by the opposite side of 9.5 is equal to sine of 75 degrees divided by the opposite side of lowercase a. If we cross multiply, we will get a times sine of 51 degrees is equal to 9.5 times sine of 75 degrees. Dividing both sides by sine of 51 degrees, we will get that a is equal to 9.5 times sine of 75 degrees divided by sine of 51 degrees. If we type this into our calculator, we will get that A is approximately equal to 11.81, and the units on this value are miles. The distance from the plane to JFK International Airport is approximately 11.81 miles. Alright my friends, that finishes this video covering the law of sines.